So welcome to a new week in Chemistry 30. This week we're going to continue on with equilibrium, but we're going to shift and we're going to talk about equilibrium of acids and bases. We're going to start with a little bit of a review. Here there are three pictures, and we want to identify which one is the best description of what happens when we take hydrochloric acid and we combine it with water. So we have one here where we have this H3O plus ions, we have water, we have Cl minus. Here we have H plus ions, Cl minus, and then here we have HCl just staying together in H2O. So which of those three options do you think is the most appropriate description of what happens when HCl is placed in water? And maybe you can come back to that answer after the next couple of minutes. So remember, acids are things that taste sour, react with metals. Acids have low pHs, so from 0 to 6. Bases have high pHs. They taste bitter, feel slippery, dissolve fats and oils. That's kind of what we talked about in Science 10 and Chem 20 in terms of what acids and bases are empirically. In Chem 20, we attempted to define acids and bases theoretically, and we started to talk about different theories. Arrhenius acids-base theory is based off of entities. So Arrhenius described acids as anything that produces H+. If H+ is there, it's an acid. He described bases as things that produce hydroxide. So his is really talking about these entities being present, and in order for them to be present, they need to be present in our reactants. So we have acids, and then bases, which are either giving H pluses or hydroxide. Now, we did modify that in Chem 20 because water is polar and H plus ions can't just float around on their own. We modified that to say that acids produce hydronium ions. The hydronium ion is the acidic ion, and it's not just as simple as H+. In some units, we've been looking, like in redox, we were using H+, and that's okay because the rest of it doesn't really matter. But now that we're in acids and bases, we're going to be talking more about hydronium. If you ever do see an H+, it's still talking about hydronium. It's just in a simpler form. So we revised Arrhenius's idea and incorporated water because water is always available. And we also incorporated the idea of the hydronium ion. We learned about things that are strong acids and strong bases in Chem 20. Remember when we talk about strong acids and strong bases, we're talking about the percent ionization, or how much they actually react. So strong acids. So a strong acid are things that ionize greater than 99%. Strong bases are things that ionize greater than 99%. And that's where we spend most of our time in Chem 20. Now, where we are going to shift gears in Chem 30 is talking about weak acids. We're talking about weak bases. Remember, weak acids ionize less than 50%. So what that means is that less than 50% of this acid goes to producing hydronium and whatever the anion is. That means more than 50% is left as reactants. Weak acids reach chemical equilibrium. The rate of the forward reaction, the ionization reaction, is equal to the rate of the reverse reaction when it reaches equilibrium. Weak bases, same thing, ionize less than 50%, and they also reach equilibrium. So this is going to be a majority of our focus in Chem 30. When it comes to strong acids and bases, these are strong acids, and these are the strong bases. Strong bases, you'll notice, are just ionic compounds with hydroxide in the name. Strong acids, if you look in your data booklet, strong acids in our data booklet are things with Kas that are very large. So it says much, much, much greater than 1. Remember the equilibrium constant Kc is my concentration of products over my concentration of reactants. So in a strong acid that ionizes more than 99%, we have a lot of products. So in our chart, the strong acids are anything with very, very large Kas. And at some, we don't even really measure them because there's not much of a point. Weak acids, on the other hand, ionize less than 50%, and so they have more reactants. When you look in your data booklet, most of those acids are weak acids, where they ionize less than 50%, and their Kcs, or their Kas, because they're acids, are less than 1. The other thing that we did talk about is the difference between poly and monoprotic. Poly means more than one proton. Mono means one proton. When we talk about protons, we're going to talk about them a lot, but we're talking about H+. So a polyprotic acid is something that's able to give up more than one H+, whereas a monoprotic acid only has one to give up. So polyprotic acid, something like H3PO4, there are 3 acidic hydrogens there. A monoprotic acid would be something like HCl. There's only one acidic hydrogen. Or something like acetic acid. There's only one acidic hydrogen. One thing to note is when we're talking about some of these molecular acids, these are covalently bonded hydrogens, so these are not acidic hydrogens. The hydrogens that we're looking for that are acidic when it comes to these molecular ones are the ones that are attached to COOs. So it's either at the front or it's attached to a COO. Polyprotic bases, same thing, can accept more than one hydrogen. So hydrogen ions are H+. So if we have something like CO3 2-, that -2 tells me it can accept 2 protons. Something like NH3 can only accept 1 and become NH4+. So we can have polyprotic or monoprotic bases as well. And sometimes maybe something like H2PO4-, this is polyprotic as an acid because it can give up 2 hydrogens, but it is monoprotic as a base because it can only accept 1. The other thing is we did do some calculations with pH. We're going to do more of these in the coming weeks. But just a reminder that we have some formulas. pH is the measure of the hydronium ion concentration, and it is a logarithmic scale. So as my pH goes up by 1, my concentration goes up by 10 times. So something with a pH of 3 is 10 times more concentrated than something with a pH of 4. And something with a pH of 2 would be 10 times 10 or 100 times more concentrated than something with a pH of 4. So it is a logarithmic scale. The other thing we looked at is the pOH scale. And we saw that it is a reflection of the pH scale in that pH and pOH always adds up to 14. So when we take pH, add it to pOH, we get 14. So as pH goes up, as pH goes down, as it gets more acidic, the pOH goes up because it gets less basic. There is kind of this relationship. So we do have some formulas. pH is the negative log of the hydronium ion concentration. If I want to find the hydronium ion concentration from the pH, I go 10 to the negative, whatever the pH is, as an exponent. That's how I go back and forth between those. If I'm talking about hydroxide ions, the negative log of the hydroxide ion is my pOH. If I want to go back to hydroxide ion concentration, 10 to the negative pOH is my hydroxide ion concentration. One thing you might not have talked about in Chem 20 is what about if I want to go from hydronium ion concentration to hydroxide ion concentration? Now, in Chem 20, you probably did it as this 3-step problem where we found pH, then we subtracted that from 14 to get pOH, and then we went 10 to the negative pOH to find the hydroxide ion concentration. However, you can see from this diagram that there is just a simple one-step calculation using something from Kw. Kw is the water ionization constant, and it has to do with any time, so we have our water. So if we have a container of water, okay, and we produce, so it's at equilibrium, we produce hydronium ions and hydroxide ions. If we look at the Kc for this, or we call it Kw because it's for water, it is equal to my products over my reactants. So my products are hydronium times hydroxide over our reactants, but because water is a liquid, it's not included. So we have this Kw expression, which gives us the relationship between hydronium and hydroxide all the time. Kw has a value. It's in our data booklet. It's 1.0 times 10 to the negative 14. That's Kw. So if I have hydronium ion concentration and I know Kw, it's always this value. I can take my Kw, divide by my hydronium ion concentration, and I will get my hydroxide ion concentration. So that's where these calculations come from. It's using Kw. Here it says 1.01. We'll just use 1.0 times 10 to the negative 14. Okay, so let's get into why things are bases. So why is ammonia a base? Why is HCl an acid in terms of what they're doing? And that brings us to the idea of Bronstad-Lowry's definition of acids and bases. They came up with a definition of acids and bases based off of what those entities are doing. So they defined acids as things that donate a proton. And by a proton, we mean a hydrogen ion. And they define bases as things that accept a proton. So things that take an H+. So when we look at HCl, HCl is an acid because it gives up a hydrogen. In this reaction, water is a base because it takes a hydrogen ion. So they define these things not by the entities that are produced, but by what they are actually doing. And so that's important to note. There is a difference between acid and base and acidic and basic. An acid is really just anything that gives up a proton. A base is anything that accepts. When we're talking about acidic or basic, that's more Arrhenius theory where we're talking about entities. An acidic solution contains hydronium. A basic solution contains more hydroxide. Now here we have water. So what would water be? So let's look at each of these, which way the proton is going. So I have HCl forming Cl-, which means this is giving up an H+. That would make HCl an acid because it's giving up hydrogens, and that would make water a base because it's accepting. When we look at this bottom reaction, here we see NH3 is forming NH4+. So it is actually taking a hydrogen from water, which means that NH3 is a base, it's accepting, and water is an acid. So you'll see that water could be either an acid or a base, depending on the entity that it's paired up with. There's a name for that, and we call it amphiprotic. So an amphiprotic species can both accept or donate hydrogen ions, and water is a good example. It can accept to form hydronium, or it can give up to form hydroxide. Other examples are things like hydrogen carbonate. The H is there to be donated, or we see that it has a negative charge, so it's also able to accept. We talked previously about H2PO4-. Now this is polyprotic as an acid because it has two hydrogens to give up, and it is monoprotic as a base because it can accept one hydrogen. So an amphiprotic chemical is something that can both give up or donate, just like an amphibian can live on the water or in the land. There's two entities. So when we look at these reactions, again, we are looking at what is happening to the hydrogen. If it accepts, then it is a base. If it donates a hydrogen, then it is an acid. So that is how we look at what makes something an acid and what makes something a base. Now, there is a consequence of this. If we think about, in this example, we have hydrogen iodide, which is an acid. It gives up a hydrogen. These are reversible reactions, so they don't just occur one way. If we were to look at the reverse reaction, we would see that hydronium is now giving up a hydrogen to iodide. So these are reactions that go both ways. If I have an acid, like this hydrogen iodide, what I end up doing is I form a base. We call that the conjugate base. If I have a base, like H2O, which accepts a hydrogen, it forms an acid, which is now able to give up hydrogens. So whenever we have Bronstad-Lowry chemical equations, we're always going to have conjugate acid-base pairs, where an acid is going to be paired up with the conjugate base, a base is going to be paired up with conjugate acid. So we have this reaction with hydrogen fluoride and water. If we look at the proton, we see that it is going from HF to H2O. That makes hydrogen fluoride an acid because it's donating a hydrogen, makes water a base because it's accepting. If we look on the other side, so we look at this reverse reaction, hydronium is giving up a hydrogen to fluoride. So that means that hydronium is now an acid, and because it's on the product side, we say it's the conjugate acid of H2O, and if the fluoride ion is the conjugate base of HF. So when we look at these pairs, HF is the conjugate acid, is the acid for the conjugate base F minus, and another conjugate acid base pair is H2O and its conjugate acid hydronium. If we want to maybe identify anything that's amphiprotic, there is one amphiprotic species here, that's H2O. It can either give up or accept, although in this situation it's being a base. So there's some examples here, and there'll be more practice. Maybe we'll do this third one. Identify the acid and its conjugate base. So we need to look at the direction of proton transfer. Acids are things that donate. Bases are things that accept. And when we look at the reverse reaction, it's the same thing. Conjugate acids are going to be any products that are donating. Conjugate bases are any products that are accepting. So my conjugate acid-base pairs here are HCl and Cl minus, and NH3 and NH4 plus. You might see a pattern, but conjugate acid-base pairs really only differ by one hydrogen. So we are looking at the amount of hydrogens when we're looking at conjugate acid-base pairs. So if I want to find the conjugate base of these acids, I need to take away one of these hydrogens. So if H2O is an acid, it would give up a hydrogen. The conjugate base of this would be hydroxide. The conjugate base of nitric acid would be NO3 minus. You'll notice in your data booklet, if you look, there are columns. The first column are all acids. The second column are the conjugate bases of those acids. If we have bases and we want to find the conjugate acids, well, then they need to accept a hydrogen. So the conjugate acid of these bases is going to have one more hydrogen in order to be that conjugate acid. The other thing is we do want to look at how we can use this idea to determine where they are and what's going to happen in that reaction. So strong acids, you'll notice those are high on the chart. They have very large Kas, so way greater than 1. They go down to weak acids, so at the very bottom of your chart, they have Kas that are much less than 1. Strong acids really like to give up hydrogen ions, which means that their bases, so something like HCl, really wants to give up H+. It's kind of like Drake at the club. It wants to make it rain, makes it rain hydrogen protons all day long. Once Drake makes it rain, he doesn't really want to be rained on. So chloride ions, the conjugate base of that strong acid, is a relatively weak, strong conjugate base. Weak acids really want to hold on. So vinegar is a weak acid. It really wants to hold on in that hydrogen. It doesn't want to give it up very much. So that means that the conjugate base, CH3COO minus of that acid, is really going to want to accept hydrogens. It's going to be a relatively strong conjugate base. You'll notice there is a pattern here in terms, like when we looked at our redox reactions, we had strong OAs up here and weak OAs down here, and then strong RAs down here and weak RAs up here. When we look at our acids, it's the same thing. So we have strong acids at the top, weak acids at the bottom, and then on the right-hand side, we have stronger bases, and on the top right, we have weaker bases. This also allows us to determine whether products or reactants are favored. Just like in redox, when the OA was above the RA, that's a spontaneous reaction. Well, it's the same thing for acids and bases. If my acid is above my base, that reaction is going to favor the products. So when we look at the equilibrium between those two, that reaction will be greater than 50%, which means that we produce more products. And if we look at the Ka of that reaction, Ka is greater than 1. Or whatever, Kc, I guess. If we put the acid below the base, that reaction is less than 50%. So it favors the reactants or the reverse reaction. So there'll be more reactants. This one's greater than 50%, meaning there's more products. So the Kc for these reactions will be less than 1. So when we do these types of questions, we want to look at, so say for example, if I look at the reaction between nitrous acid and lactic acid, the conjugate base of lactic acid. So when I look at this reaction, so I have HNO2 plus C2H5OCOO minus. So when I look at this reaction, I can determine the products by looking at the conjugate acids and bases. So my acid, again, is going to donate a proton. So this is my acid, this is my base. My acid donates a proton, so I'm going to have NO2 minus, and I'm going to have C2H5OCOOH. So I have my conjugate base of that acid and my conjugate acid of the other base. It's kind of how I can determine the products. But the other thing we can do is determine whether products or reactants are favored and what that percent reaction is going to be. The rule here again is my acid is above my base, so that's greater than 50%. So this will be a greater than 50% reaction, meaning my products are favored. So when we compare those, so we look at where they are relative to each other, we determine the reaction, and then we determine the percent reaction based off of their relative positions. If maybe I want to do a different one, so let's look at the reaction between this oxalate ion and between lactic acid now. So I have C2H5OCOOH, that's my acid. I have my oxalate ion, which is a diprotic base. It can accept 2, that's my base. So my acid gives up a hydrogen ion to form C2H5OCOO minus, plus my base accepts 1. So I have my conjugate base and my conjugate acid. My conjugate acid, you'll notice, is amphiprotic. You can both give up or accept. But we can determine that percent reaction by looking at where they are. So here my acid is below my base, so it'll be less than 50%, which means that it will favor the left-hand side or the reactants. So in summary, again, acids are things that donate protons. Bases are things that accept. Acids and bases always come in conjugate acid-base pairs. We can determine the percent reaction by looking at their relative positions in our chart. If the acid is above the base, it favors the products. Acid below the base, it favors the reactants.